Okay, so today we're going to continue talking about positive definite matrices. For the first half of class, the second half of class will just be on the quiz. So as I said in the email yesterday, or the announcement yesterday, the quiz will have two questions. One where you have to compute a power of a matrix, and then the other problem where you had to find an orthonormal matrix that diagonalizes the matrix. And the second problem will show up in one of the examples that we do in class today, just with different numbers pretty much. But the same idea will apply, and you won't have to go as far in the quiz as we do in class today. But it's built off of material that we talked about in section 6.4. So it's not illegal for me to put it on the quiz. Okay, so we're talking about positive definite matrices in the previous class. I was kind of rushing through a lot of it because I didn't have a lot of time, and I wanted to go through proof, and I didn't have time to do it. So probably wasn't very clear what I was talking about. But just as a reminder, an n by n matrix S is going to be said to be positive definite if we have that S is a symmetric matrix and every single eigenvalue ends up being positive. These are particularly nice types of matrices, and eventually we'll come up with a theorem that will classify or give you a number of different ways you can test to see whether or not your matrix is positive definite or not. And so we looked at one example where we showed that it was positive definite. Just from the definition alone, if you want to show something's positive definite, you can just check and make sure that every eigenvalue ends up being positive. So that's what we did with this example. We took the determinant of this matrix subtracted by lambda times the identity. We computed the eigenvalues. We ended up having two distinct positive eigenvalues, lambda 1, or lambda is equal to 1, and lambda is equal to 7. They're both positive, so that means that it's positive definite. Furthermore, this is a symmetric matrix, so we know that the eigenvectors are going to be orthogonal to one another. That'll show up later and on the quiz. And so this is where we ended class. I didn't really do a good job of explaining the proof of this. But we have the following proposition, which I don't really know how useful. Like, it was throwing me. The statement of this proposition was throwing me off a little bit because I didn't think it was like. To me, it seems like kind of clear. Like, it says that the signs of the eigenvectors of a symmetric matrix are going to be the same as the signs of its pivots. And so what initially threw me off was the word pivots, because when I think of pivots, I think of like the terms on the diagonal after doing reduced row echelon form. But if you think about the entries on the diagonal and reduced row echelon form, it's always going to be 1 or 0. So I was like, well, there's only like plus or 0. But when it's talking about pivots, I think it's just talking about what happens if you reduce your matrix into triangular form or upper triangular form and stop there. So I have like a little example written out before going through the proposition. So when it's talking about the pivots, it's just saying like if you were to reduce this matrix into upper triangular form, it would look like the following. So you'll take row 1, multiply by -2, and then add it to row 2. So you would get the matrix 1, 2, 0, -3. And so the pivots in this case are 1 and -3. But then this is why I don't think like the proposition tells you that much, because I mean, you can just read off that the eigenvalues are going to be 1 and -3. So of course the signs of the pivots will agree with the signs of the eigenvalues, right? Regardless, we'll go through this proposition because I think the idea is kind of neat in proving this proposition. So we're saying the eigenvalues of a symmetric matrix are the same as the signs of its pivots. So the idea is the following. We're just going to look at a specific example and go from there. So we have this symmetric matrix S, which is equal to 4, 3, 3, 4. And so if we want to reduce this matrix into upper triangular form, we can apply multiplication by elimination matrices like we did in the beginning of class this semester. And so it looks like the following, right? If we wanted to get rid of this 3 here and this 3 here, we can do multiplication via these elimination matrices. And so one of the important parts of this proof is the fact that multiplication by these elimination matrices doesn't change the determinant of S. Elimination matrices are either lower or upper triangular, and the diagonal entries are always just 1. So the determinant of elimination matrices are just 1. So if you do this product, the determinant is just going to be 1 times 7 times 1. So it doesn't change the determinant at all. And so if you just write a general X, like if you look at this, you can kind of see that X should be equal to -3/4 if you wanted to cancel out this 3 here and this 3 here. But we'll just leave it as a general X for now. And so if you follow through with this multiplication, you end up getting the following matrix. And so we're going to use some ideas from calculus to prove this, or really just one idea, the intermediate value theorem. And so the idea is we're going to look at two specific x values. If we let x be equal to 0 in this equation, then we end up just getting the original matrix back. We end up just getting like 4, 0 plus 3 is 3, 0 plus 3 is 3, and then 0 plus 0 plus 4 is equal to 4. So if x is equal to 0, nothing changes. So we end up just getting that L transpose is just equal to the original matrix S. And the eigenvalues of this matrix are 1 and 7. So they're both positive. And then the other x value of interest is going to be x is equal to minus 3 over 4. So if we let x be equal to minus 3 over 4, it's equivalent to just reducing our original matrix into a diagonal matrix. Or really, it would be like upper triangular, but we lucked out in that like the diagonal entries are the same, the off-diagonal entries are the same. But yeah, applying, if you let x be equal to minus 3 over 4, you just end up getting this diagonal matrix. And you can see that the eigenvalues of this diagonal matrix are going to be 4 and 7 over 4. And so this is the idea, or this is where the intermediate value theorem comes into play. And so the reason why we wrote this out in an equation, this matrix out as an equation, is we want to see what happens as x varies from 0 to minus 3 over 4. And if we let x vary from 0 to minus 3 over 4, the eigenvalues that we're finding based off of these various matrices are going to vary continuously. But the big idea is we're going from eigenvalues that are positive to eigenvalues that are positive. And so if there were an x value where we ended up having a negative eigenvalue, what this would mean is that at some point in time, the determinant of this product would have to be equal, or would have to be less than 0, right? Or it would have to be equal. Well, there would have to be a point where it's equal to 0, and then a point where it has to be less than 0, right? But the point is, like, this multiplication never changes the determinant. Like, the determinant is always going to be equal to 7 no matter what this x value is going to end up being. So there's never going to be an x value where the determinant ends up being equal to 0. So there's never a point where these positive eigenvalues can end up being negative. So like the sign has to be maintained for every single x value between x is equal to 0 and x is equal to minus 3 over 4. So that's what this paragraph is saying. So just summarizing, in order that any eigenvalue change signs, it must equal 0, or it being the determinant must equal 0 for some x. This is impossible because this product doesn't change the determinant at all. So the eigenvalues can't change sign at any point. So it's kind of like conceptual what's going on. And again, we're using the intermediate value theorem from calculus, right? It's saying if we switch signs in the eigenvalues from positive to negative, there must be a point in time where the determinant is equal to 0, which is a contradiction because this could never be equal to 0. It must always be equal to 7. Okay, so that's the idea of the proposition. I don't really think this is like the preferable way of thinking of positive definiteness, but I thought I'd go over it anyways. Are there any questions about, I guess, the idea behind the proof of this theorem or proposition? Okay, if not, we'll move on. So there's other useful criteria for determining whether or not it's going to be positive definite or not. Oh yeah, there's just like this other theorem. I don't think we're going to use this too much. Well, actually, in like one of the application chapters we're going to be looking at later on, we're going to look at Markov matrices, which will involve steady state vectors. And so I guess it kind of has to do with like looking at the size of eigenvalues and how they kind of converge to diagonal matrices. But this is like just a cool theorem. It's not going to show up on an exam or anything like that. But we have the following statement that says that if lambda is an eigenvalue of an n by n matrix, then if you consider the difference between lambda and this diagonal entry of your matrix, so AJJ, this is going to be strict. Well, it's going to end up being less than or equal to the length or the absolute value of the sum of all the terms off of the diagonal of that row. And so what this is saying, like, this looks like a complicated mathematical statement. But what it's really saying is that like this lambda, the eigenvalue lambda is going to get, like, it's going to be pretty close to the diagonal matrix or diagonal entry of your matrix, so much more than it is to the entries that are going to be off of the diagonal entry for a row. So it's like this idea of diagonal dominance. So like the lambda, like if you had like a huge lambda value here or like a huge value AJJ here, like this is equal to like 1,000 or something like that. It's telling you that lambda has to be close to 1,000 as well. That's the idea. Again, this is just like a neat theorem. It's not really going to show up in this class, but I thought I would mention it just to give you an intuition. Like, I guess what you should take away from this is like the eigenvalues should be kind of close to the diagonal entries of your matrix, which should play into your intuition, because we've noticed there's like a lot of correlation between diagonal entries and corresponding eigenvalues. Okay, so that's just like a neat aside, I think. So this is the last application, or one of the last things we're looking at for positive definiteness. This is like a quick section, so we're not talking that much about things. But we're going to look at a specific application of positive definite matrices and how you can use like diagonalization to understand them. And you get like a new decomposition, which has its utilities. So this is what we were talking about in section 6.4, and it's going to show up on the quiz today. So if we have a symmetric matrix S, then we know from the previous section that S is going to have a set of orthonormal eigenvectors that leads to the following decomposition. So we can write S is equal to Q times lambda times Q inverse, where the columns of Q are orthonormal vectors. And then we have that lambda are the eigenvalues of S. Maybe I should say more. So Q are orthonormal vectors, but they're just the eigenvectors normalized. So you compute the eigenvectors corresponding to S. Those make up the columns of Q, and then you normalize those vectors, and that will give you what Q ends up being equal to. And so because Q ends up being an orthogonal matrix, we have that the transpose of Q just ends up being equal to Q inverse. So that's going to make computations a lot easier. And so if we have that S is a positive definite matrix, then this tells you that the eigenvalues of S are going to be positive. Therefore, the entries on the diagonal of lambda are going to be positive. And so because the entries on lambda are positive, it means you can take the square root of those entries. And so with this in mind, as the entries of lambda are positive, it's possible to write lambda is equal to d squared, where the diagonal entries of D are just going to be the square roots of the eigenvalues, right? So you just take lambda and you apply the square root to each term. And this is like something we already did in the example. I think it was the last example we did in section 6.4. We found the square root of a matrix by taking the square root of lambda. But if a matrix is positive definite, it's ensured that this can always be done. If we had negative eigenvalues, we'd have to go into complex numbers, which we don't like. And so we end up getting the following decomposition. So if we rewrite lambda as d squared, it tells us that S is equal to Q times D times D times Q transpose. And so you can write this in a clever way. Instead of writing Q times D, you can rewrite this as D transpose times Q transpose transposed. And so D is a symmetric matrix. It's just a diagonal matrix. So D transpose ends up just being equal to D. And so you end up getting the same matrix multiplied by itself, except this first matrix has a transpose. So if you let A be equal to D times Q transpose, it tells us that S is equal to A transpose times A. Which, I mean, it's kind of like, well, who cares that we can write S in this way? But it'll be useful for certain proofs and certain propositions, like the next one we're going to talk about. Any questions about this slide before moving on? Oops. Okay, it should be pretty intuitive, right? We're just using diagonalization again. Okay, so we have the following proposition, which will also allow us to determine whether or not a matrix ends up being positive definite or not. So we have that if S is positive definite, then we end up having that X transposed times S times X ends up being greater than 0. So strictly greater than 0 for all X that are not equal to 0. And so the proof of this isn't really too terrible. So the main idea is the following. So as S is positive definite, this implies that S is going to be invertible. The reason why we know that S is going to be invertible is because S is positive definite. It means that all the eigenvalues are positive, which means S doesn't have any zero eigenvalues. Because it doesn't have any zero eigenvalues, it means that S is going to be invertible, right? So all positive eigenvalues implies S is going to be invertible. Furthermore, we have the following. So we have that. Okay, so this goes back to a proof that a proposition we showed in section 4.2. I don't know if people remember it, but we end up having the following. So we have S is equal to A transpose times A from the previous slide, right? Because S is positive definite, we know that S can be written as A transpose A from the previous slide. So what this means is that the null space of S is equal to the null space of A transpose times A, just due to this equality here. And then we showed in section 4.2, way back in the day, that this is equal to just the null space of A. So we showed this in section 4.2. So the null space of A transpose times A always just ends up being equal to the null space of A. And so because S is invertible, we know that this null space is just equal to 0. And so this is going to imply that A has full rank. We don't know that A is necessarily a square matrix, so we can't say it's invertible, but we know that it has full rank. So it has a trivial null space. And so how we can utilize this information is the following. So this is the importance of this A transpose times A decomposition. It's going to make computations for S a lot easier. So we end up having that X transpose times S times X. If you rewrite S as A transpose times A, we get the following. And then you can rewrite this in the following way. So we have X transpose times A transpose is really just equal to A times X transposed. And then this is going to be times AX. Right. So this is just the, like A times X is a vector, and then A times X is a vector. So this is really just the dot product of two vectors. So this is equal to the norm squared of AX. And because A has full rank, we have that this quantity, like AX, is going to be non-zero for any vector X that's not equal to 0. So we have that this is greater than 0. So this is greater than 0. Let me be more specific. So this is greater than 0 for X not equal to 0. And this is due to the fact that A has full rank. Or maybe let's write it like this. This is due to the fact that the null space of A is equal to 0. Okay, so this verifies that X transpose times S times X is strictly greater than 0 as long as X is, there should be X not equal to 0, obviously. If you plug in X is equal to 0, you just get 0, right? Okay, any questions about the proof of this proposition? Okay. Yeah, so this gives you another way of determining whether or not a matrix will be positive definite or not. Of course, like if you show that you have this product and if it ends up being less than or equal to 0, it means that your matrix can't be positive definite. So I'll write out like all the different ways of checking positive definite later on, after we're done with this. Okay, so I have like 5 to 10 minutes left. So I might have to rush through this next example, but I kind of want to just get to the applications next week. And I don't want to have to talk about positive definite. So let's go through this next example and then we'll be good to go, start on the quiz. Okay, so this example is just looking at the decomposition we established a couple of slides ago, except we're going to be looking at a specific positive definite matrix. So we're going to let S be equal to 3 minus 1 minus 1, 3. And we want to factor S in terms of A transpose times A. And so if we want to, factoring S in terms of A transpose times A just involves performing diagonalization. So we want to determine what S, the eigenvalues and eigenvectors of S, what are those going to be, and then go through with the diagonalization. So we have S is equal to Q lambda Q transpose, which is equal to Q times D Q transposed, where Q is an orthogonal matrix, hence why we're using Q transpose instead of just Q itself. And we have A, this vector, like this matrix A that we ultimately want to find is equal to D times Q transpose. So this is the goal. We want to find this. Okay. In the interest of time, I'm going to do a couple of shortcuts. I'm just going to tell you what the eigenvalues and eigenvectors are going to be. So we end up having lambda 1 is equal to 4 is one of the eigenvalues. And then lambda is equal to 2 is the other eigenvalue. So this is lambda 2. The corresponding eigenvector to lambda 1 ends up being the following. So you end up getting v1 is equal to minus 1, 1. The corresponding eigenvector to v2 or lambda 2 ends up being equal to 1, 1. And so what we want to do to these eigenvectors, this is what you're going to be doing on the quiz, is like you could define Q to have the columns as these orthogonal matrix vectors, like the columns would be these orthogonal vectors, but that doesn't actually give you an orthogonal matrix, which is kind of unintuitive. For it to be an orthogonal matrix, the columns have to be orthonormal. So you take these vectors and then you normalize them. So you take V1 and you write Q1 is this equal to V1 over the length of V1. Let me do a little bit more space here. And so this is just going to, the length of V1 is just the square root of 2. It's the square root of 1 squared plus 1 squared. So this is 1 over the square root of 2 of minus 1, 1. And then you do the same thing with V2. So you end up getting that Q2. The length of V2 is this the square root of 2 again. So this is 1 over the square root of 2 of 1, 1. So just to summarize, if you want to find an orthogonal matrix Q, or orthogonal matrix Q that diagonalizes your matrix, you find the eigenvalues, compute the corresponding eigenvectors, and then you normalize those eigenvectors. So you have orthonormal vectors. And so that tells us that Q, this matrix Q ends up just being, the columns end up being Q1. That looks like an A, hold on. Q1, Q2, and so you can write this, you could factor out a 1 over the square root of 2 because everything has a 1 over the square root of 2 applied, but I'm just going to write it like this. So this is minus 1 over the square root of 2, 1 over the square root of 2. So that's our Q1 showing up here. And then Q2 is 1 over the square root of 2, and then 1 over the square root of 2. Okay, so that's how we find what Q ends up being equal to. And then we have that Q inverse. Because this is an orthogonal matrix, Q inverse is just equal to Q transpose. And if you take the transpose of this matrix, it's actually a symmetric matrix, so you end up just getting Q back again. So this ends up being equal to, the transpose of Q just ends up being minus 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2. So this is an example of a matrix where the matrix is its own inverse. So I guess that makes it a projection matrix. You multiply Q by itself, you get the identity. Oh wait, no, that's not a projection matrix. Never mind. Forget I just said that. Okay, so we end up getting the following. And so we end up having that S. Oh, let me do one other thing. We said what Q was, but we didn't find what D was equal to. D is like the easiest part, right? So D is just equal to the square root of lambda. So we have Q. Q is the hard part. D is the easy part. So we have D is equal to lambda to the 1/2 power. Lambda is just the diagonal matrix where the entries are the eigenvalues. So we have 4 and 2. So this is the 4, 0, 0, 2 to the 1/2 power. This is just equal to 2, 0, 0, square root of 2. And so we have what D is equal to, and we have what Q transpose is equal to. If we want to find what A is equal to, we just multiply D with Q transpose. And so we have finally that A is equal to D times Q transpose. This is equal to 2, 0, 0 times the square root of 2 multiplied by minus 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2, 1 over the square root of 2. Okay, and if you multiply these matrices together, you end up getting the following. So I'll just write it out. It ends up being minus the square root of 2, square root of 2, 1, 1. And the multiplication really isn't that bad. So this is the answer it's looking for. You find A by multiplying D with Q transpose. And then I guess you should verify that your answer actually works. So to verify that your answer actually works, you do the following. So the main reason why we care about A in the first place is we want to show that our original matrix is equal to A transpose times A. And so if we take the transpose of A and then we multiply it by A, we should get our original matrix back. So that's how you can check. So we have A transpose times A. A transpose is equal to minus the square root of 2, 1, square root of 2, 1. And then you multiply by the minus square root of 2, square root of 2, 1, 1. And so you can see if you do this row dotted with this column, you get minus square root of 2 times minus square root of 2. That'll give you 1. And then you have 1 times 1. So that'll give you 2 plus 1, which is 3. Minus square root of 2 times the square root of 2 is minus 2. Plus 1 gives you minus 1. And then you end up getting a symmetric matrix, right? So this is minus 2 plus 1 will give you minus 1. And then you get 3 here as well. And so this is equal to S. So everything worked out fine. Okay, any questions about this example? Okay, and I'll say it one more time. So if you have to find an orthogonal matrix, Q, what you do is like you find the eigenvalues. Sometimes they're provided for you. And then you have to find the eigenvectors. Once you find the eigenvectors, you just have to make sure they're orthonormal, right? It's symmetric with distinct eigenvalues. So the eigenvectors are independent. They end up being orthogonal. So from there, you just have to find the norm. You just have to normalize them. And that'll give you your Q. Okay. So I'm going to stop recording and then I'll pass out the quiz.